Hi and welcome. I'm trying to learn particle physics, today the symmetry of a standard model. After we've done it, we're going to the ECU 10 training. The ECU 10 is here, and if you participate in the ECU 10 training, then it's better there on the screen. Hermann Weyl took this idea of phase symmetry a step further and supposed that every electron might be twisted by a different amount and still remain the same. Assuming this, and almost by magic, all four of Maxwell's equations emerge. We're talking about that the electrons and how the universe could be changing their position, but they're keeping still the same energy, or what was it? Noether's theorem shows that charge conservation too arises from symmetry. Fundamental particles have a property called spin, and just as position doesn't matter on a frozen lake, what is known as the spin space doesn't change physical calculations. I mean that the lake keeps its same state. The lake, they had a picture of a lake with a frozen ice on top of it, and there a puck on it. And whether there's a puck on it or not, it doesn't change the condition of a lake. As the standard model has developed, so the symmetries of interest have become more subtle. But Noether's theorem has been the gift that keeps on giving. It is hard to conceive, for example, the electrons, the particles that run through wires to power electronics, and neutrinos, which fly through us by trillions every second, without leaving a mark, are in some sense the same particle. Neutrinos primarily interact through the weak force, which controls nuclear fusion in the Sun. Okay, these neutrinos, which are passing the trillions per second through the human body, just as an example, are controlled through the weak force, or interacting through the weak force. And it is this weak force which controls the nuclear fusion in the Sun. But the weak force is indifferent to whether a particle is an electron or a neutrino. Switch them around and weak interactions will be the same. Okay, weak force interacts with electrons and with neutrinos. This symmetry produces conservation of quantity called a weak isospin that, like electric charge, can be used to label particles and predict how they will behave. Okay, let's just, in the 1960s, researchers found that electromagnetism and the weak force could in fact be generated by single symmetry, what became known as the electroweak theory, a keystone of the standard model. Breaking that symmetry into two separate pieces produced a bunch of new interactions, along with the prediction of a new particle, what we now know as the Higgs boson. We know that it was discovered in 2012, let's do it again. Waited a half century for the confirmation of this prediction, which stemmed directly from the sort of considerations Noether's theorem introduced into physics. It came eventually with the discovery of the Higgs at CERN Large Hadron Collider in 2012. Okay, breaking that symmetry into two separate pieces produced a bunch of new interactions, along with the prediction of a Higgs boson. What symmetry? The symmetry, researchers found that electromagnetism and the weak force could in fact be generated by single symmetry. Electromagnetism and weak force, what became known as the electroweak theory. Okay, there's the electroweak theory. We have it mentioned previously, but we didn't really understood it there, and we don't understood it here. Don't really understand it here. The electroweak force. Okay. The other pillar of the standard model is the strong interaction, which holds individual protons and neutrons together. The weak interaction reacts with the neutrinos and the electrons, and they are passing over time through them, and it is this weak interaction which controls the nuclear fusion in the Sun. And it can be combined together with electromagnetism to become electroweak. And then there is the strong interaction, and that holds the protons and the neutrons together. The quarks that make up these particles are labeled with one of the three colors, red, green, and blue. Okay, first of the three colors are red, green, and blue. And they are just labeled with that, maybe we don't have that color. Shift all of the colors by 1 and all strong interactions will remain exactly the same. Color symmetry leads in what might at first seem to be a tautology to conversation of color. Since that idea was first introduced, work on the nature of a strong force has found that all particles in nature exist in states without color, white effectively. Is now the color just something to make it easier to distinguish them, or do they have a color, or how do we come up with a color? Color symmetry leads in what might at first seem to be a tautology to conservation of color. Since that idea was first introduced, the work on the nature of a strong force has found that all particles in nature exist in states without color, white, effectively. Okay, they don't have a color, they're effectively without a color. Protons and neutrons are examples of particles called baryons that consist of 3 quarks, one red, one blue, and one green. The universe as a whole seems to be colorless, just as it is electrically neutral, and the symmetry of a strong force is what makes particles like protons and neutrons possible in the first place. Now, what symmetry do we talk about? Symmetry of a strong force. I didn't really get it now. Physics is now at the point where new theories are built on the assumption of a fundamental symmetry and an informed guess about what that symmetry might be. Unification is the holy grail of physics, the drive to develop theories that can be described everything in just a few, albeit possibly outstandingly difficult equations. Okay, we just try to find theories to describe everything. And we know if a theory works here, it will also work there. I think that's the whole point of the symmetry what we're talking about. What sort of symmetry might unify the electroweak and strong forces we don't yet know, but the search for such a grand unified theory is an active area of physical endeavor. Okay, in the next part we will continue here with the grand physical endeavor, with a grand unified theory. But it is an area of physical endeavor. If you were here for particle physics, you can go directly to the next part of particle physics. We will do now the ECU 10 training. If you participate in the ECU 10 training, then it's very honest. Go to still stand. Arms next to us, hands from the fists, and doing the flat game. Bring the fists down. Hold it. And again up. And hold it. Again down. And up. And again up. And last time. Next exercise, fist next to us, we count 5 money check, bring the wrists up. And again down. There are 3 rules. The first rule is that we're stopping immediately as soon there is pain. The second rule is that we're going only as fast as we can go with a little bit of effort. And the third rule is that we're not overdoing it. Last time down. If you want to take a break, then do it. We just want to strengthen, not to exhaust. I'm going to use now a tennis racket. A tennis racket is light, it has just around 300 grams. Whatever you use, do it in accordance with our 3 rules. We're starting with the Manikaneko with the lower arm in, with the elbow, take the lower arm and go slowly. On with one side, it's slow. Slowly over, and then on to the other side. Now we're saying the slow arm mode. Now with your light. Small arm in, move your elbow, slowly over to one side, and over to the other. Now with the lower foot. Now take bracket or whatever on the top, lift up, once over, and then back in half step over. And another time. And now with the palm facing upwards, the same basically. The garbage truck's grab arm. And yeah. And again with the palm facing upwards. Now, you can use a t-shirt or whatever, or sock, as you have good force onto it. Bring the wrist up. And down. And up. Again down. And again. And change. Press again. Bring the wrist up. And again down. Again up. And the last time down. Now just press onto the good force in neutral position. All on the outside. And wait for the ECU tension. Thank you very much, and until next time.